Okay, I'm going to show how to solve this problem. The first step is to find the M matrix. So the M matrix will be a 4 by 4, and we already know that the bottom row is going to look like this. This right side here is just going to be the coordinates of the end effector, so we can see that's going to be, well, in the z direction it's going to be 0 because this is it's displayed on a flat surface, and it doesn't go into the z direction at all, as you can see. In the y direction, we go up 6, down 1, so we're at 5, and then down 2 more, so we're at 3, so the y value is positive 3. In the x direction, we go over 3, and then over another 3, and then over 1, so that's 7. So this value is 7. And so this is going to contain the rotation matrix. So the first thing we do is we look at what is the x value, and we're going to basically put the x value right here. And as we can see, the x of the end effector is located in the minus x direction of the space frame. So what we do is we write the minus x vector in the position, in the first position. And the y vector, well, we can see that's just opposite the space y vector, so we just put the negative of that in there. And then the z direction of the end effector is in the same direction, so that is just the regular z vector. And that's the M matrix. Okay, so in order to find the S values, the first thing I did is I labeled each one of the joints either R for revolute or P for prismatic, and then the number of the joint next to it. Another thing to note is that the axis of rotation, the axis of positive rotation, is labeled with these orange arrows, and when it's just a dot, that means that the axis of rotation is in the z direction, in the positive z direction, pointing out of the page. So let's get started. So the first 3 values in each column of S is the axis of rotation. So for the first joint, it is in the positive y direction, so it'll look like this, 0, 1, 0. And this value is also called W1. And so then to get the next 3 values, first we find another vector called Q1, which is just the displacement of the center of rotation. So here the center of rotation is at positive 2 in the y direction, so it's just going to be this, 0, 2, 0. And then the last 3 values in this column is going to be minus W1 cross Q1, which is the cross product, which if you don't know how to do that, you can look up calculators or guides. But for these 2 vectors, it's going to be 0 because these 2 vectors are pointing in the same direction. So that's what we're going to put in the last 3 values here. Okay. For the next one, we have a prismatic joint, and for prismatic, because there's no axis of rotation, because it doesn't rotate, you put zeros here, and instead of doing the cross product, for the last 3, you just put in the direction of the joint, basically, which in our case it's in the y direction, so we do 0, 1, 0 to indicate the y direction. Next we have another rotating joint, and this one is in the positive z direction, so we do 0, 0, 1. So we have W3 equals 0, 0, 1. And then we do Q3, and this is going to be 0, 6, 0, because that is the location of the center of rotation. And then we find minus W3 cross Q3. And for this, you can use the right-hand rule, which is you point your 4 fingers in the direction of the first vector, which is going to be in the positive z direction because the first vector is W3. And then you curl them towards the second vector's direction, which is the y direction. and then whichever direction your thumb is pointing, that's the direction of this cross product. So in this case, it's pointing in the minus x direction. But then also, to include the negative, you flip that. So for us, it'll end up being pointed in the positive x direction. So what we're going to get here is 6, 0, 0. And another thing that you can do is just use an online cross-product calculator, and you can just plug in a bunch of sets of 3 vectors and keep doing it over and over again for practice, and eventually you'll see how to compute the cross products. Okay, so the fourth one is again a prismatic joint, which, as you'll see, I mean, the prismatic joints end up being a lot easier than the revolute ones because you don't have to compute the cross product. Okay, so then the fifth one is in the positive z direction again. Okay, so then you have W5 is equal to 0, 0, 1, and then Q5 is equal to, okay, so this one's a bit harder. We have to figure out the coordinates of this. So I guess it's going to be 5 in the y direction and 3 in the x direction. Okay. Q5. Okay, I'm going to have to use a calculator for this one. Okay, so I've found this cross product using an online calculator. And yeah, I guess that's something else I should have mentioned, is that as long as you don't need it for a test or anything, you should just be able to use a calculator or a program to compute the cross products for you. I mean, if they're very difficult like that one. Okay. So on to the sixth joint. So this one is in the minus y direction, so we do 0, minus 1, 0. And then Q6 is equal to, okay, so in the x direction it's 6, and in the y direction it's 6, minus 1 is 5, and that's it, so 5 and 0. Okay, I'm gonna look this one up quick. Okay, so I found the cross product, so I'm gonna copy it into here. Okay, and finally on to the last joint. So this is also revolute. It's in the positive z direction, so it's going to be 0, 0, 1, and 0, 0, 1. Okay, so in the x direction, it is 7, and in the y direction, so it's 5. And then the cross product. Okay, I'm gonna go look this up again. Okay, so here's the cross product, so I'm gonna copy that in here. Okay, and that is the full S matrix. And so when we talk about S, the important thing is really the columns. So this is the second column, this is the third one, fourth one, all that. And that's really the most important thing for the S matrix, because it's not really treated like a matrix. You basically just deal with its columns when you actually put it in the formula. And I'll copy over the M matrix just so we can have it on the same page. Okay, and so now we put all this together to find the space transformation matrix, which is called TS. And this transformation matrix basically tells you the angle and orientation and position of this end effector depending on the angles of each of these joints. And it works for any angle for each of the joints. So the formula starts off with M, and then you right multiply by the matrix exponential of the bracket of S1 times theta 1. And you can look up the bracket notation if you haven't seen it before. And you basically just do that for each joint. And that's how you get this formula for the transformation. And something else to note is that each of these S columns are a 6x1, but once you put it in the bracket, it becomes a 4x4 matrix. And each of these thetas are just the angle of each of these joints. And so each of the angles are just like a single value, not a matrix or anything. And there you go, that's it. Also, once you take the matrix exponential, so this right here, this whole thing is a 4x4 matrix. You take the matrix exponential, it's still a 4x4, and M is a 4x4, so it's just a bunch of 4x4 matrices all multiplied together. So the end result is also going to be a 4x4 matrix, and it's going to be this transformation. And that's it.